Welcome back to the Deep Dive. You want to understand the modern frontier of artificial intelligence, but, you don't have time to sift through every single white paper published this week. So our mission is to cut through all the marketing hype and give you that competitive advantage by going straight into the engineering mechanics that are, well, actually driving the breakthroughs. If we look across the entire generative AI landscape in 2025, one word really captures the moment: convergence. I mean, it doesn't matter if you're using an LLM to debug a massive code base, or a system to generate a 30-second movie trailer, or an engine synthesizing perfectly realistic speech. At the foundation, they are all running on the same basic engine, the transformer architecture, and they all rely on the precise tokenization of continuous signals. It's really just one unified field of engineering now.
And that standardization, it means the competitive bottleneck has fundamentally changed. The basic architecture is a known quantity, right? So the secret sauce has moved entirely away from inventing new attention types and towards two specific, highly disciplined areas. First, precision data engineering, the complex high-tech recipe for the data that goes in. And second, massive optimized infrastructure, the physical reality of the clusters that makes this scale even achievable.
And that is the deep dive for today. We are unpacking the specific recipes, the math, the physics, the hardware constraints that are enabling all the latest LLMs, MLLMs, audio, and video generation systems. We're going to show you exactly how they are engineered for scale and for quality. Okay, let's unpack this. And as always, we start in the source, text. We've always known that, data quality dictates performance, but that axiom isn't just a truism anymore. It's a specific, highly mathematical engineering discipline. We're looking far beyond simple web crawling now, diving into pipelines like FineWeb and Dolma.
Right. The old way was pretty blunt. Crawl everything, remove the exact duplicates, run some simple filters. But FineWeb showed that this blunt approach is fundamentally lossy. The central innovation they introduced is what they termed rehydration. Look, we know that you have to deduplicate to prevent the model from memorizing specific training examples that just ruins its ability to generalize. But here's where it gets really interesting. If you use standard deduplication, you accidentally eliminate these high utility signals. Yeah. Think about like a standard Python library manual. It might appear 5,000 times across GitHub, documentation sites, forums. If you remove 4,999 of those near duplicates, you've just thrown away the overwhelming signal that this document is highly valuable to the community.
So the frequency isn't noise that you have to scrub. It's actually an implicit signal of quality that you need to leverage.
Precisely. To handle this, they use sophisticated hashing techniques. It's similar to giving every document a unique fingerprint, which allows them to quickly identify these large clusters of near duplicate documents. But instead of just deleting the entire cluster, they analyze the size of that cluster. That's their popularity signal. They then select the single highest quality document from that cluster and use the cluster size to upsample it during training. They're basically saying, this document is important, so we'll spend more compute time on it. They boost the true signal while avoiding training on redundant tokens.
That is extremely clever. It moves data curation from simple subtraction, just deleting noise,
to strategic addition.
Exactly, boosting validated signals. But not all bad data is a popular signal. Sometimes it's just garbage. And that's where structural filters, the famous gopher rules, come in. What are the engineering specifics of those filters?
These are simple, brutal, and they are so effective. They remove documents that just look structurally broken. For example, they remove anything outside the 50 to 100,000 word count range. If it's too short, it's probably a comment or a list of links. If it's too long, it's often a broken serialization or a giant poorly formatted dump file. Another crucial filter is the mean word length check. They reject text where the average word length is outside the 3 to 10 character range.
And why is that?
Well, if the average is less than 3, you're likely looking at noisy, non-meaningful text. If it's significantly over 10, you're almost certainly looking at massive code dumps, broken URLs, or, non-natural language sequences that just confuse the tokenizer.
And the symbol-to-word ratio. I love that one. That's the indicator of absolute web sludge, right?
It is the universal marker for structural filth. If the ratio of symbols like curly braces, hash marks, angle brackets to actual words exceeds a specific threshold, like 0.1, you are looking at dirty HTML, machine-generated log files, or scraped boilerplate. They just toss those documents entirely.
Okay, so we've sanitized the input to ensure quality, but integrity is just as critical for trustworthy evaluation. And that brings us to Dolma's requirement for test-set decontamination. Why is it so vital to check your training data against your benchmarks?
Well, if you skip decontamination, your metrics are basically meaningless. You have to check for n-gram overlaps, these small sequences of words between your entire multi-trillion token training corpus and common evaluation benchmarks, like the reasoning problems in GSM-8K or the code tasks in Human Evil. If the model has seen a solution or even the full text of a test question during training, it hasn't learned to generalize, it's just memorizing. Dolma's pipeline rigorously identifies those contaminated training documents and just removes them. And this ensures that when an LLM scores well on a benchmark, you, the listener, can actually trust that score reflects genuine generalization and reasoning capability, not just rote recall.
So if we've fixed the fuel, the data, the next step is upgrading the engine itself. We know the standard objective, next token prediction, or NTP, where the model tries to guess the very next word, suffers from this teacher-forcing myopia. It's like a student only cramming for the next pop quiz, never thinking about the final exam. It just loses the high-level semantic plan.
And that takes us into the cutting-edge pre-training objectives designed to break that myopia, and the chief among them is continuous concept mixing, COCO-mix. The entire goal here is to teach the model to reason in high-level ideas, not just low-level tokens. The mechanism relies on a tool called a sparse autoencoder, or an SAE. This tool is used to decompose the model's internal hidden states, all those complicated calculations it performs.
Black box.
Exactly, the black box. It breaks it down into interpretable, high-level feature directions. You can think of these as specific defined concepts.
So it's like, instead of the hidden state being one giant messy vector of numbers, the SAE is actually saying, okay, this part means I am starting a function definition, and this other part means I am arguing the positive side of a political debate.
That's it, exactly. It gives the latent space structure and interpretability. The model is then given a dual task. Not only predict the next low-level token, but also predict the future continuous concepts that must guide the overall generation. And this forces the model to maintain a high-level semantic plan over long sequences. If you tell it to write a sonnet, it maintains the structural concept of sonnet across dozens of lines. And that results in massively improved reasoning performance and, critically, coherence.
That seems so much more robust than just trying to guess the next word. And they layer complementary strategies on top of this, right? Like multi-token prediction or MTP, where it guesses T+1, T+2, and T+3 simultaneously.
MTP is great, yeah, because it forces the model to capture a broader local context. But my favorite complementary method is future summary prediction, FSP. This tasks the model with predicting a compressed abstract summary of the next block of text it's going to generate. By anticipating the gist, or, the overall arc of the future narrative, it acts as a very strong regularizer. It stops the LLM from simply wandering off track after a few paragraphs of perfect fluency.
Let's transition now, because the convergence we talked about means these principles aren't just for text anymore. They apply directly to multimodal LLMs, MLLMs, and audio, as long as you can figure out how to tokenize those signals properly.
Right. When we look at MLLMs, the visual processing architecture has become very standardized. It's really a three-part machine. You have a vision transformer, a VIT encoder that consumes the image, a frozen, powerful LLM for reasoning and text generation, and the absolute linchpin, the modality connector in the middle.
That connector, whether it's a Q-former or a perceiver resampler, that's essentially the universal translator, isn't it? It takes the complex visual features from the VIT and compresses them down into a sequence of tokens that the LLM's frozen text processing engine can understand and process as if it were a foreign language.
That's the architectural bridge. But again, the competitive advantage comes right back to data. They realized that simple image caption pairs, this is a picture of a dog, are insufficient for teaching complex reasoning. You need interleaved data like Obelix or MMC4, where images and text are interwoven in a coherent narrative flow, like a web page or a richly illustrated textbook.
And if you're pulling interwoven data from the web, the images are going to be messy. So you need precise filtering to make sure there's narrative coherence. Give us the math behind that coherence filtering.
This is a beautiful piece of engineering logic. They calculate the cosine similarity between the semantic embeddings of consecutive images, MGI and MG1. Essentially, they are just asking, how similar are the high-level concepts in these two pictures? The genius is in the boundaries they set. If the similarity is too low, say below 0.1, that means the images are completely unrelated. The sequence just jumped from a picture of a cat to a picture of the Eiffel Tower. That's noise, and they remove it.
Okay. If the similarity is too high, say above 0.9.
Too high means they are redundant. If the similarity is near 1.0, it's probably 2 frames of the exact same buffering spinner or a near duplicate image. Training on that is just wasted compute. By filtering for that middle ground, that range between 0.1 and 0.9, they are specifically filtering for progression. They want visual diversity that maintains a strong semantic link, forcing the model to learn sequencing and narration.
That's how you inject critical thinking right into the data pipeline.
And speaking of critical thinking, let's talk elevator reward. Instead of relying purely on expensive, slow human annotators to check if the MLLM is hallucinating visual details, they turn the AI back on itself.
It's the ultimate efficiency hack, AI policing itself. They use a highly specialized pre-trained MLLM itself as a reward model. This model evaluates the output of the primary generative MLLM, focusing specifically on spotting hallucinations, mentions of objects or actions that are demonstrably not present in the input image. The generative model is then optimized using preference learning techniques to maximize that automated reward score. And this is incredibly effective at reducing visual hallucination rates and scaling up alignment efforts without relying entirely on costly human feedback loops.
Now, to audio. Sound waves are continuous, meaning they have near infinite data points. You can't just feed that raw waveform into a transformer, you have to tokenize it. And this is why neural audio codecs like encodec and DC are such a massive breakthrough. They are the tokenization layer for sound. The way they solve the problem of requiring an impossibly huge vocabulary for high-fidelity sound is through something called residual vector quantization, or RVQ. Think of it like artistic layering. If you try to capture every single nuance of high-fidelity audio with a single vocabulary book, that book would have to contain millions of entries, which is just unmanageable. RVQ uses a cascade of smaller, manageable codebooks. The first codebook captures the gross features, the general melody and rhythm, the big shapes of the sound. Then, the residual error, the difference between the original sound and what the first book captured, is passed to the second codebook. The second book only has to worry about the finer details and smaller errors. You stack 8 or 12 of these books, each correcting the residual error of the last, which results in high fidelity using small, discrete token vocabularies.
It's brilliant like sketching in layers, where each layer only focuses on the mistakes of the previous one. And let's not overlook the specific architectural detail that ties the math to the physics of sound. The use of snake activations in the Descript audio codec.
It's an engineering insight that should really stick with you. Standard neural network activations are smooth, but sound waves are inherently periodic. So the DAC uses a periodic nonlinearity in its layers. Yx equals x plus sin 2x.
Why does that matter so much?
By embedding a periodic function into the very structure of the network, the model gains an inductive bias that matches the physics of sound. It implicitly understands the periodic nature of waves, which significantly improves phase coherence, how well the wave structure aligns, and that leads to noticeably higher audio quality and fewer artifacts.
And finally, a key performance breakthrough in audio generation: the shift toward flow matching, or rectified flow, as a superior alternative to traditional diffusion models.
What's fascinating here is how it addresses inference speed. Diffusion models essentially learn this wandering stochastic path from noise back to the clean data. They take hundreds of steps to complete the generation. Flow matching, conversely, learns a deterministic ordinary differential equation that maps noise to data along a straight line.
A straight line is always faster than a wandering path.
Exactly, because the trajectory is straight and deterministic, the generator can produce extremely high-quality audio output in very few steps. We're talking 10 to 20 iterations. That is a massive immediate win for inference speed and cost across the board and without sacrificing fidelity.
Let's add the final dimension time. Let's move into video, which adds exponential complexity. And video immediately forces us to confront the biggest challenge of all: infrastructure and distributed training.
Right. When you look at state-of-the-art video diffusion transformers, or video DDTs like OpenSora, they treat the video as a 3D volume of patches height, width, and time. If you try to run full attention across that entire volume, the $2 computational complexity is just prohibitive. The compute required scales quadratically with the sequence length. So the engineering solution is factorized spatiotemporal attention. Instead of calculating attention across the whole 3D cube simultaneously, they break it down. The model first attends spatially, building coherence within a single frame. Then it attends temporally, looking across different frames to ensure smooth, consistent motion. This factorized approach is really the only way to manage the astronomical computation demands of high-resolution, long-duration video.
But even with that factorization, these models are enormous. So the efficiency breakthrough in training them, the open store recipe, relies on progressive resolution and duration scaling, which is just a fancy name for curriculum learning. You don't start training at 4K resolution. That's way too expensive. Training begins cheaply on low resolution, short clips, say 144p video lasting only 2 seconds. This teaches the model the gross motion and the fundamental physics of the scene at a minimal cost. Then, and only then, do they progressively scale up, eventually fine-tuning on the long, high-fidelity clips, 720p or 16 seconds.
It's the engineering equivalent of making cheap storyboards before you shoot the final, complex scene. And this curriculum massively reduces the total compute required to reach high quality, which is essential because none of this fine-grained data filtering or multi-token objectives or video factoring is possible without specialized physical infrastructure.
And this is where the physics meets the architecture. We're talking about training runs that require thousands of GPUs. The solution is 3D parallelism. We have to break the model down along 3 distinct axes.
The first is tensor parallelism, or TP, which splits the weights interlayer. It's extremely bandwidth intensive and must happen quickly, so it stays within a single server node, communicating across ultra-fast NVLink connections. Then you have pipeline parallelism, PP, which splits layers internode to scale the model depth. This is more latency sensitive because the micro batches have to flow through the entire chain of servers.
And finally, to handle memory, we have the zero redundancy optimizer, or ZERO.
Zero is purely about memory efficiency. It partitions the vast amounts of memory required, the weights, the gradients, the optimizer states, so that no single GPU has to hold a redundant copy. It effectively pools the aggregate memory of the entire cluster, making it possible to train models so large that even one layer wouldn't fit on one GPU.
So when all these thousands of nodes are talking to each other, especially for synchronization in those tensor parallelism steps, what is the communication backbone that makes this even remotely possible? Is it standard Ethernet or something else?
For the largest foundational training runs, InfiniBand still dominates. And the core reason is RDMA, or Remote Direct Memory Access. It means the GPUs can write directly to the memory of other remote GPUs, completely bypassing the CPU and the operating system kernel. The GPU is essentially elbowing the main computer aside and saying, I've got this. This cutout is critical for high-frequency synchronization tasks because it just eliminates latency from the software stack.
And its hardware-level losslessness is absolutely vital, right? That's where the straggler problem comes in.
Yes. InfiniBand uses credit-based flow control, which guarantees zero packet loss. In a cluster with thousands of interconnected components, a single dropped packet forces the entire system to stop, wait for the retransmission, and resynchronize. This is the straggler problem, and it can drastically reduce the effective speed of your entire multi-million-dollar cluster. InfiniBand is designed at the hardware level to eliminate that bottleneck.
So given that necessity, where does the hardware design become dictated by the AI architecture? What's the most surprising detail about the physical wiring?
That would have to be the rail-optimized topology. This is where hardware engineering serves the model's needs directly. Remember, tensor parallelism is the most bandwidth-intensive communication, requiring corresponding GPUs across different nodes to talk constantly. The rail-optimized wiring ensures that all corresponding GPUs, say, all GPUs, across every server node in the cluster are connected via the absolute minimum number of switch hops. They are organized on a dedicated rail. This guarantees that the critical, high-frequency, all-reduce operations required by tensor parallelism receive the necessary high bandwidth and low latency, maximizing the speed of the training cycle.
Wow. We have journeyed deep today. We moved from the high-level convergence of the transformer all the way into the deep trenches of data curation, understanding how to use popularity as a signal with rehydration, to cutting-edge objectives like CocoMix that solve high-level reasoning, the bizarre but necessary coherence filtering math for multimodal data, and finally, the physical constraints of a rail-optimized InfiniBand network.
The central finding is unavoidable. The competitive edge in generative AI is no longer the transformer itself. It's the complex, highly specific systems built around it, the universal tokenization layer for every modality, and the precision curriculum induction processes that feed the models and the high-speed networks that host them. So, here is a final provocative thought for you to explore. If the physical network topology, like that rail-optimized InfiniBand, must be custom designed to suit the model's current communication patterns, what happens when the next architectural breakthrough, perhaps a totally new sparsity mechanism or an attention-free system, demands a fundamentally different physical infrastructure? How tightly linked will the constraints of the silicon and the wiring become with the future architectural breakthroughs in AI?
Something to ponder next time you hear about a new foundation model breakthrough. Thank you for joining us for this deep dive. We hope you feel thoroughly informed.